Hello, I'm Christian from Group 12. Caleb, Kylan, Yuki, and I will be presenting Project 3 for ESC 220. So let's first start out by defining what ductility is. Ductility is simply a measure of a material's ability to plastically deform before it breaks. On the picture on the left, you can see that the bolt has been stretched past that point, and you can see how on the picture on the right we have the starting point of our material and the end point right as it's about to break, and you can see that percent elongation is the ductility. Now let's move on to define what tensile strength is. Tensile strength is simply the max amount of tension that a material can withstand before breaking. This value is normally measured in megapascals, and as you can see on the picture on the left, we have here our necking event. That would be where it's approaching its tensile strength, or the most tension that the material can withstand before it breaks. And obviously here you can see how this material has gone past that point and has actually cracked. So now let's move on to the iron dagger. So we can see here that the situation for the iron dagger is that the iron dagger is assumed to be just a cylinder, and we are stretching it from an initial diameter of 5 centimeters to a diameter after the elongation of 3 centimeters. Now, using these diameters, we can find the cross-sectional areas before and after the elongation. And as we can see here, the area of a circle is just pi r squared. So we're going to do that on both sides, and find that our area before the elongation was 19.635 centimeters squared, and the area after the elongation was 7.069 centimeters squared. Now, using these areas, we can calculate the percent cold work. So after plugging the percent cold works in, we can find that the percent cold work is 64%. Now, this is a significantly high number, which would mean that the ductility would decrease by a significant amount, and the strength would increase by a significant amount. We can also find the tensile strength, and we did this using the values that we found in Project 1, and we end up with 1167.04 newtons per centimeter squared. And now I'll hand over the presentation to Caleb to talk about the aluminum dagger.
To solve for tensile strength, we will use the formula force tension divided by the original cross-sectional area. In order to solve for the tensile strength, we first need to solve for the original cross-sectional area. We will use the formula pi r squared, as this dagger is a cylindrical shape which has a side profile of a circle. We will do pi times 2.5 centimeters squared to get 19.635 centimeters squared. We can now divide the force tension, being 4,515.6 newtons, which we got from the first lab, and divide it by 19.635 centimeters squared, the original cross-sectional area that we just solved for, to get a tensile strength of 229.98 newtons per centimeter squared. To find the ductility, we first need to solve for the final cross-sectional area. We will use the same formula that we used to solve for the initial cross-sectional area, but we will use the new radius being 1.5 centimeters. We will do pi times 1.5 centimeters squared to get 7.069 centimeters squared. Now we can use the formula original cross-sectional area minus the final cross-sectional area, all divided by the original cross-sectional area. We will then multiply by 100 to get a percent. This means we will do 19.635 centimeters squared minus 7.069 centimeters squared, all divided by 19.635 centimeters squared, and multiply all of that by 100 to get 64% for the ductility. I will now pass it on to Yuki and Kylan. where they will discuss cold working.
Welcome back to part 3, project 3 for material science. I'm Yuki and I'm in group 12. Today I'll be talking about cold work hardening of steel. So to start things off, what is cold work? So cold work is the plastic deformation of metal below its recrystallization temperature, which increases in strength and hardness but decreases in ductility. Common methods seen for cold work is rolling, drawing, hammering, and forging. I've placed visual representations on what that would look like in the real world. Starting from left to right, we have rolling, forging, and hammering. Next up is cold work of steel in microscopic mechanisms. The first equation is the equation for area reduction. In this case, R would be equal to 1 minus the final diameter all over the initial diameter squared equals to 1 minus 0.6 squared, which would equal to 0.64. Next equation is the equation for true strain, which would be natural log of initial cross-sectional area all over the final cross-sectional area, which equals to natural log of 25 over 9, which would equal 1.02. Now, these numbers are just examples to show what the equation would look like when used. Now back to cold work, which introduces a high density of dislocations. Dislocations interact and entangle, forming dislocation networks and subgrain boundaries on the metal or material used. Movements of new dislocations becomes harder, which forms higher yield stress. Grains become elongated and distorted in the direction of the deformation. Now, after cold work, the material would elongate grains, higher dislocation density, dislocation walls from subgrains, strong internal stress fields hinder slip. And for engineering implications, cold work steel is stronger but less ductile, suitable for tools such as springs and blades like the dagger from Project 3 that we are talking about. To restore ductility, you would need annealing processes. Trade-off between strength and toughness is crucial for this part. And I will be handing over the presentation to Keelan.
Based on the information, aluminum's ductility was reduced by 64%. This satisfies the requirement that ductility had to be greater than 15%. Based on that ductility of 64%, the tensile strength does not meet the requirement of 800 megapascals. When the aluminum undergoes the cold working, the atom planes slide, causing dislocations to entangle. This reduces empty spaces within the lattice structure of the material, causing tensile strength and yield strength to increase. The presence of all those dislocations makes it harder to deform, which increases those strengths. Cold working on aluminum also decreases ductility. It does so when plastic deformation adds dislocations to the structure of the material. It causes the material to break easier because the dislocations are entangled. It also causes grain boundaries to elongate and flatten, which make it more difficult for the material to undergo any more plastic deformation. This means when you stretch the material, the dislocations can not move anymore, meaning the material will break much easier. Cold working also increases the material's electrical resistivity. This is caused by the increased number of dislocations, which scatters the electrons.